Hey guys, so quick video about hydrogen bonds and why is it so important, and you're gonna hear about the hydrogen bonds all semester long. They are everywhere, they do everything, they're amazing. It's almost like protein. So now that we talked about the hydrogen, oxygen, water molecule remaining charges, we talked about all of this. You've seen in your manual that the oxygen is represented usually like that, with hydrogen's atoms on either side here. And the remaining charges are a giant -1 here and two positive remaining charges there, right? And of course, you have to think that water is a bunch of those together, a lot of them. And so now we know that the hydrogen part of one water molecule will face the oxygen part of another one, right? Because those remaining charges will be attracted to each other, right? Right? So that's how those hydrogen bonds are formed. Those remaining charges from hydrogen, part of the molecule of water, is linked to is not attached but kind of related, linked to the remaining negative charge from the oxygen of another water molecule. So now that that is clear, I want us all to think of temperature as movement, because that's all it is. Temperature is molecular movement. You may not perceive it, but this hand, that skin, is not immobile. Like I'm moving a little bit here, but what I want you to realize is all those atoms are vibrating constantly. The table, the board here, that board, the atoms are vibrating. I cannot go through because my atoms are too big, my hand is too big, and there's more cohesion between them than like with my hand, so I cannot go through it, right? But they are vibrating. Nothing is immobile. Nothing. The only way to have immobile things is the absolute zero, which is extremely cold. It's like minus 200 something degrees. It's extremely cold. That's when molecules don't move anymore. But everything above absolute zero, which is minus 200 plus degrees, everything moves. And in water, so everything is on a gradient again, once again, between absolute zero, no movement, and complete movement, that is absolute speed, like light. Everything is on a gradient between those two. Now, if you think of water, all those water molecules are moving. They're not moving, they're moving enough to break some of the hydrogen bonds sometimes. Because if you don't move enough, if you reach 0 degrees Celsius, which is freezing temperature, all the hydrogen bonds between all water molecules are formed, and so they arrange themselves in that crystal that you can see in one of the slides. Now, when that happens, it's solid water. You cannot go through it anymore because because all the bonds, hydrogen bonds, are made, so there is a solid, compact mass of water that you cannot penetrate. Now, when the temperature rises above zero, the movement of those water molecules is strong enough to actually break some of the hydrogen bonds. But they're constantly reforming, rebreaking, reforming, rebreaking. But at any given moment, there are several of them, millions of them, that are formed. When you put your hand in water that is above the freezing temperature, you can go through it because those bonds are not all formed, so you can find ways between them, right? So now what does that tell us? Frozen ice. Ice is always frozen. it's a misnomer. Water that's frozen, it's still moving. It's vibrating, but really slowly. Water that is vibrating more allows for the fluid movement that we know of water. If we go and vibrate it so much that we reach 100 degrees Celsius, which is simply an indication of vibration of molecule, that's temperature, it's to the point that no hydrogen bond remains. If no hydrogen bond remains among between water molecules, all those water molecules are individualized, and what does happen? They vibrate so much that they climb in the atmosphere, and that's called steam. So the boiling of water, it's literally the moment when no hydrogen bond remains. And when that's the case, water changes phase to the vapor phase from the liquid phase. And that's all there is to it. The hydrogen bond's importance to water, this is it. The movement of water due to its temperature indicates how many hydrogen bonds are formed at any given moment. That in turn indicates the state of water. All of the hydrogen bonds are formed? Ice. And that goes from 0 degrees Celsius to infinite negative temperature until absolute zero. Between 0 and 100 degrees Celsius, enough water molecules are moving that some of the hydrogen bonds are breaking, but at any given moment there are still hydrogen bonds formed, and that leads to the phase being liquid. Above 100 degrees Celsius, too hot, all the molecules are moving so much, no hydrogen bond is remaining. Therefore, the water is steaming, vapor phase. And that's it. That's really it. And so by understanding that, you start to understand why several things are true. Water in form of ice takes more space than water liquid. Because all those hydrogen bonds are formed, the crystal is fixed and takes the maximum amount of space water can. Now, if you break some of those hydrogen bonds, you can fit water molecule in between, and so you take less space, right? Now you also understand why when you fill your mug of tea with hot water and you before you sip your tea, when you dip your tea bag in the water is that high in your mug, and you will notice that next time you make some tea. That's a cup. That's your hot water level. Come back when it's cooled, it will be lower. Why? Because the water molecules move less, and so they take less space. So hot water is always takes more space than cool water. So you can literally see that next time you make a tea. I do that every day. I make my tea or my coffee. You fill the mug with water. If you let it cool, diminish. So to see that effect strongly, boil your water, boil it hard. When it's boiling at 100 degrees Celsius, dump it in the cup, put the tea bag in. With the tea bag in, leave it in, let it cool, come back, don't take your tea bag out, and look at the water level. It will have diminished. That is also why, another reason, when you fill your cup with water, normal water, just not boiled, and you add an ice cube in it, you see the ice cube hanging in the water, right? And once the ice cube is gone, the water level hasn't changed. Just because the ice cube displacement of water is equal to the volume of the water that's in the ice when it would be liquid. So all that additional volume outside, above the level of water, like icebergs, all that additional volume is literally all what's more than what the water in ice form will take as space as liquid. Because that area here, that volume, is exactly the volume of that ice cube in shape of water instead of ice. That's literally why. So now you see that ice cube and you look at it and you're like, oh, that's the hydrogen bonds. Because it takes more space as ice as in water, it has less density, so it's float. Because density is just the amount of molecules per volume. So you have that amount of molecule in that volume, but when it's in liquid phase, it will take only that space. So liquid water is denser than ice water. And that makes perfect sense, right? It's all about that organization of molecule. And if you look at the diagram of those molecules of water when they're in ice, you will see that they take more space just simply due to the conformation of those hydrogen bonds forming those crystals. And so you have to take that much space. But when those hydrogen bonds are breaking due to temperature, there is more space available for the water molecule to enter. And so liquid water takes less space. That's why ice floats. There you go. You learned some cool stuff today. I'll see you next time.